we're going to look at a few examples of some applications that will put Rolle's theorem and mean value theorem into some kind of real world context with some of these. So in these next few examples, I'm just going to kind of state once, and if you have some of these in the homework, you'll notice that they'll state like, assume that the distance function being described is differentiable, which the differentiability will imply the continuity. So I just stated here, let's just assume that the distance functions that are described in these problems below are continuous and differentiable on the needed intervals that we're going to be looking at here. So I may restate it when we get into the problems, but just kind of starting off there. So number one says, consider a train leaving a station where f of t is this distance function. So again, we're going to assume this is the continuous and differentiable function on the intervals that we need here coming up. So it's the distance that the train is away from the station, t hours after it's left. So it's how far it is from the station. Suppose that after traveling for a while, the train engineer realizes that there's a mechanical problem and he or she has to return to the station. Let A be the time when the train left the station and B be the time when the train returns to the station. We want to apply and interpret Rolle's theorem. All right, so again, kind of by the assumption here, so let's just sort of real quickly write out. So we're going to assume that we have continuity from the time that we left and then to the time we returned on that closed interval, and that we have our differentiability on that open interval. Now, for Rolle's theorem, the last condition that we need, let's think about it here. So we're just kind of assuming the first two. Now, does f of A equal f of B? Well, it's the distance that the train is from the station, and if A is when we left the station, and then B is when we've returned to the station, in both of these situations, at time A and time B, we are a distance of 0 from the station. So those two are, in fact, equal to one another. So we can apply Rolle's theorem. So we've met our three conditions. So now let's apply and interpret Rolle's theorem. So by Rolle's theorem, what we know is that there has to be a point in time. So there has to be a time, we could call it C, but there has to be some time in the interval from A to B, from the time we left to the time we came back. So there has to be some time between A and B where f prime of that time, so f prime, is equal to 0. Well, the derivative of a distance function, the rate of change of distance, that's our velocity function. So this is the rate of change of our distance function, how fast the distance is changing with respect to time, is our velocity function. So essentially what we have discovered is that there has to be some point in the time when the train has left the station, it drives out for a certain distance, and then it comes back. There had to be that instant when it was neither traveling away from nor was it traveling back towards to the station. There had to be that instant in time when the velocity was actually equal to 0. Pretty intuitive, right? If it leaves the station and comes back, there had to be that instant when it did actually come to a stop. And so that's what we have here. All right, let's look at another example. So when iPads first came out, this is a true story, by the way, a friend of mine refused to get one because he was convinced the government would start recording times between tolls and then just issue you speeding tickets. And I'm not so sure that he was so far off from the reality on something like that. So suppose you pass through one toll at 2 p.m., and then you pass through another toll 40 miles away at 2:30 p.m. So we have probably our pretty good intuition, which is kind of what my friend would have said, but let's be real specific and think about how mean value theorem could be applied in kind of a formal way here to issue you a speeding ticket. All right, so let's just kind of define a distance function here. So let's just say we'll let our f of t be our distance function. It'll be the distance that you've traveled after kind of our initial position here. We'll be passing through that initial toll. So we're going to let that be, that is not spelled right. Okay, I should just erase that. No wonder that, yeah, initial, sorry, yikes. Let that be our distance after the initial toll that we went through. So I guess I'll just say where, so we're saying that at time equals 0 corresponds to 2 p.m. when we went through that toll. Okay, so again, we're going to, kind of like last time, we're going to assume, so we're going to assume that f is going to, that we're going to have our continuity here on our closed interval, so from 0 to a half hour later, so time is going to be time in hours, and we're going to assume that we have our continuity and differentiability with this distance function. All right. Now, this one's mean value theorem. Okay, so these are the only two things that we really need for mean value theorem. So we have these two. Okay, so then what we're going to now say is, then by the mean value theorem, what we know is there has to be some point in time, call it C, call it whatever you want, there has to be some point in time in that interval from 0 to a half an hour. So in that interval from 0 to a half hour later, where, well, what has to be true in that interval? It's where the derivative, so f prime, is going to have to equal the slope of the secant line. So slope of the tangent line equals slope of the secant line, or instantaneous rate of change equals the average rate of change. So where that would equal f of a half an hour minus, so the f of b minus f of a, which is 0, all over b minus a. So what we're really saying is that there has to be this moment in time where, if we think about this side here, so this is where our slope of the tangent line, or in this case, this is our velocity. So this is the, maybe even just in words, that instantaneous, is that right? Velocity. So there has to be some point when that instantaneous velocity is equal to, so when that would equal, and then what we have here on the right hand side, this is the slope of the secant line, or the average rate of change. So this is our average velocity, or the average rate of change. And so if we think about what this computation would look like, so the distance we've traveled after a half an hour, we're now 40 miles out, minus our initial position distance, we're letting that be 0, and then divided by, of course, this 1/2 minus 0. So 40 divided by a half is like 40 times 2, and so that is equal to 80. So what we have now shown is that there has to be some moment in time where your instantaneous velocity was equal to 80. So you were speeding. Okay, so that's what we now know. So therefore, I'm sorry if you can hear my dog barking. Someone just rang our doorbell. So at some point, you must have been going 80. Must have been going 80 miles per hour. Okay, thus you were speeding and you get the ticket. Okay, so the last example here, It says, at a horse race, at Arlington Racetrack, there are two horses that start a race at the same time and tie. Does that necessarily mean that at some point in the race, the two horses were traveling the same speed? If so, use an appropriate theorem to show that. All right, so with this one, let's start off and let's define a couple of functions here. So let's let f of t be the distance of horse F. So this is going to be the distance of horse F. And let's let g of t equal the distance. I can write here. Sorry. So let's let g of t equal the distance of horse G. All right, so then what we're going to do is we are going to define, gosh, my handwriting is terrible today. Not that it's so great always, but we are going to define, that looks better. We're going to define h of t to be a distance function that is the difference in the distances of horse F and horse G. And we're going to also so a couple of things we need to define here. We're also going to let capital T, let's let that equal the time it took the horses to finish. So the time to finish, because they did tie, so it would be the same for both. So the time to finish the race. All right, so once again, we are going to, by assumption here, we're going to assume that our h of t, this difference of two distance functions, so we're going to assume that this is continuous on our closed interval from 0 to t, and that we are differentiable on our open interval from 0 to capital T. All right, so we've satisfied the first two criteria for really both theorems. Now we have to decide, is this going to be more of a Rolle's theorem or is it the more general mean value theorem? Well, let's think about what we know about h of 0 and h of capital T. Okay, so h of 0 is equal to, f is the first one, I guess. So h of 0 is just f of 0 minus g of 0. So this is just their initial position, right? Pretty boring. So these are both 0, so obviously that's 0. And then the time to finish the race, that's what capital T is. Now, I don't know what the full distance of the track was, right? But I know that, I keep wanting to write the G one first for some reason. I know that the differences in their distance at time t, because they're at the same point, I know that this is equal to 0 because they tied, right? And so at time t, they both finished. So basically this was equal to, if we want to write something out, I mean, we could say that both of this is the full, whatever the length of the race is. So f of capital T is whatever that race distance is, because capital T is when they finished, and g of t, they finished at the same time. This is also whatever that, full distance of the race is, that's the distance. And so obviously when you subtract these, we end up with 0. Okay, so what we now know is both h of 0 and h of t are equal to 0. And so this now tells us that we have a Rolle's theorem situation. So we know that Rolle's theorem is going to apply here. All right, so what does Rolle's theorem tell us? Rolle's theorem tells us that there has to be, so by Rolle's theorem, we know that there is a point, or not point, well, a point in time. Let's just say there is a time. There is a time in this interval from the time 0 to the time that they finish. So there is a point in time in this race where h prime of t is equal to 0. Well, h is f minus g, and we can take the derivative term by term when you have adding or subtracting. So this is going to be f prime of t minus g prime of t is equal to 0. And then if you add one of those to the other side, the g prime of t rather, we would have f prime of t is equal to g prime of t. Well, f again, go back to the very beginning, f is the distance function of horse f. So the rate of change of that distance function, that is our velocity function. So this is the velocity function. I'm going to put like a little subscript here, f here, of horse f. And then similarly, the derivative of the distance function of g, that is derivative of the distance, rate of change of that distance is velocity, but this is the velocity for horse g. So there has to be some point in time, by Rolle's theorem, there had to be this point when they were traveling the same speed. Okay, so yes, does that necessarily mean that there was, so kind of the original question back up here was, does that necessarily mean that at some point in the race the two horses were traveling the same speed? Yes, it does. So, final answer, yes, by Rolle's theorem.